Section 4.6, Molecular Structure and Polarity. Now, all the drawings we've done so far, we're describing molecules in 2 dimensions, but obviously, molecules are actually 3-dimensional. We need a way to be able to describe bonds in terms of distances or lengths, angles, and relative arrangements in space. So this is where Vesper theory comes into play. Sometimes people call it Vesper theory, since that's a little easier to say. I learned it as Vesper theory, and this stands for valence shell electron pair repulsion theory, or Vesper theory. And this theory is a way to predict the 3-dimensional shapes of molecules. Now, the assumption of this theory is that electrons repel each other, so they're going to try to be as far as possible in 3-dimensional space, right? It's like when you have 2 of the same ends of a magnet and you try to put them together and they bounce off each other. Kind of the same idea with electrons, right? They don't like being next to each other, so they are going to try and get as far apart as possible. So first thing we need to do is we need to know how many electron domains, or regions that contain electrons, there are on our central atom. So an electron domain can be any of the following: a lone pair, a single bond, a double bond, or a triple bond. Each counts as 1 domain. Double bonds do not count as 2. Triple bonds do not count as 3. Each of these counts as 1 electron domain. So for example, carbon dioxide, our central atom carbon, has 2 double bonds next to it. Therefore, it has 2 electron domains. Here in ozone, our central atom oxygen has 1 single bond, 1 lone pair, and 1 double bond, so it has 3 electron domains. Here we're looking at the molecule ammonia. Our central atom nitrogen has 3 single bonds and 1 lone pair, thus it has 4 electron domains. So let's look at the electron domain geometries. So electron domain geometries, this is the geometry a molecule has based solely on the number of electron domains. So 2 electron domains gives the shape of linear. So the central atoms being shown in the center, and then the terminal atoms are being shown on the outsides here. 3 electron domains, trigonoplanar. 4 tetrahedral. 5 is trigonal bipyramidal. And 6 is octahedral. And so these are the ideal geometric shapes to get the electrons as far away from each other as possible, given the number of electron domains present. Okay, now just to assure some people here, you're not going to have to memorize these. There will be a sheet on the reference sheet. I'll talk about it in a few minutes. Okay, now bond angles. Bond angles, so this is the angle in between atoms. They are based on the electron domain geometry. So each of these 5 has a typical bond angle. So linear, 180 degrees, right? 180 degrees between these 2 bonds. That makes sense. Trigonoplanar is the shape that kind of looks like a peace sign. So we've got 120 degrees in between each of the bonds. Tetrahedral kind of looks like a tripod. So this is a little hard to visualize in 2-dimensional space. But this atom right here sticks up, and then these 3 go out evenly, kind of forming like a tripod-like shape. So there is 109.5 degrees between each of these bonds. Trigonal bipyramidal is unique in that it has 2 different bond angles. So trigonal bipyramidal is kind of like someone took trigonoplanar and they shoved it onto linear. So you've got linear this way, and you've got trigonal planar this way. So you've got a 90-degree bond angle between here, and you've got a 120-degree bond angle between these 3 peace signs right here. And technically, you could also say you've got 180 degrees between these 2, but that's not always marked that way. It could come up, but generally speaking, we're just going to focus on 90 degrees and 120 degrees. And then octahedral looks like this. It's a 90-degree angle between all of the 6 atoms here. Again, you could make the argument you've got 180 degrees between here and here, but primarily we're focusing on the 90-degree bond angle between each of these bonds. Now I do want to highlight that thing we noticed with trigonal bipyramidal. There are 2 different types of angles because there are 2 different positions. So these right here are called the equatorial positions. I like to think of them, they're on the equator. They are right in the center. So these are the equatorial positions. These 2 are called the axial positions. They stick up out along the y-axis. They are perpendicular to that trigonal plane. Now this is not something I'm expecting you to memorize. I just wanted to note it because it will come up when we look at some of the molecular geometries in a few slides. Okay, So now molecular geometry is the actual shape the atoms make in 3 dimensions. So electron domain geometry is the shape molecules have just based upon their electron domains. But the molecular geometry is the actual shape the atoms themselves make. Now sometimes the electron geometry, or the electron domain geometry, and the molecular geometry match, but they do not always match. And the reason for that is because of lone pairs. Lone pairs affect the molecular geometry shape. The reason for this is that lone pairs are a little more, they have a bit stronger of a repulsive force than bonds do. So lone pairs will distort the geometry a little bit because they have, it's more concentrated electron. It's a more concentrated region of electrons, so it pushes the bonds a little further away and it kind of distorts or bends the shape a little bit. So for example, something that has 4 electron domains, we would expect it to be tetrahedral, but if it has 2 lone pairs, it takes on what's called a bent molecular geometry, where these 2 bonds get pushed a little closer to one another because the lone pairs are kind of extremely, they have very strong repulsion forces, and they push those bonds away from the lone pairs, and it pushes the bonds closer together. Okay, so let's look at these charts and how you would go about using this to find the molecular geometry. So this, you'll have an abbreviated version of these charts on the reference sheet for the exam. So if you've got 2 electron domains, your electron domain geometry is linear, and it doesn't matter how many lone pairs you have, the molecular geometry is going to be linear. Now with 3, we start to see it get a touch more complicated, so it's going to get a little more complicated each time we add a domain. So 3 electron domains gives a trigonal planar electron domain geometry, 120-degree bond angle. Hybridization, we'll learn about that in chapter 5, so don't worry about that right now. Lone pairs, so if you've got 0 lone pairs, the molecular geometry matches the electron domain geometry. This goes for all the examples we're going to look at. If the molecule has no lone pairs, the molecular geometry matches the electron domain geometry. Here, if you've got 1 lone pair, the geometry is what's called bent 120. So this lone pair will cause these bonds to be slightly closer to one another, which will cause the bond angle to be a little less than 120 degrees. Okay, when we get to 4, our electron domain geometry is tetrahedral. We have 3 possible molecular geometries: tetrahedral, trigonal pyramidal, and bent. So the ammonia example we looked at is trigonal pyramidal. It's got 4 electron domains, 1 lone pair. Water is an example of bent 109.5. All right, when we get to 5, our electron domain geometry is trigonal bipyramidal. So we have 4 different potential shapes: trigonal bipyramidal, seesaw, T-shaped, and linear. And you should also notice here that the lone pairs always go on equatorial positions to maximize the distance between the lone pairs. Okay, and finally, we've got 6 domains, octahedral. So the approximate bond angle is 90 degrees. We have 5 different shapes: octahedral, square pyramidal, square planar, T-shaped, and linear. All right, knowledge tech question. What is the molecular geometry or shape of the SF4 molecule? So take a few minutes, draw the Lewis structure of the SF4 molecule, and then see if you can come up with the answer here. Okay, the correct answer is A, seesaw. So let's talk about how you would solve this. First, you need to draw the Lewis structure. So you've got 6 electrons coming from sulfur, 28 coming from fluorine. So I'll draw sulfur as my central atom. I'll draw single bonds to the fluorine atoms. Now my next step is to fill in the octets of the terminal atoms. So I'm going to fill in the octets of my fluorine atoms. After I do this, I need to count. How many electrons have I used so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I have used 32 electrons. I had 34 at the start, so I've got 2 extra. So those last 2 electrons, put them on the central atoms, and sulfur is in the 3rd period or lower. Sulfur can have additional electrons. It can be hypervalent. So this is the correct Lewis structure. Okay, so now we want to look at our central atom sulfur here. How many electron domains does sulfur have? 1, 2, 3, 4, 5. Sulfur has 5 electron domains. So to figure out the geometry, first you would go to this chart and you would say, okay, my central atom has 5 electron domains. Now you move down the chart and say, well, how many lone pairs does it have? Well, it's got 1 lone pair. So 5 electron domains with 1 lone pair gives the molecular geometry seesaw. So this makes A the answer, seesaw. All right, now bond angles with lone pairs, I do want to briefly comment on this. Now, as I mentioned, bond angles are based on electron domain geometries. So for example, something like ammonia, it has a tetrahedral electron domain geometry, so it has a bond angle close to 109.5. However, the lone pair takes up extra space, which pushes the hydrogens slightly closer together so that H and H bond angle is 106.8 degrees instead of 109.5. So that's why we generally just put a less than sign, because we're just going to generalize here and say, well, lone pairs generally compress the bond angles, but it's different depending upon the molecule. This also happens with double bonds, just to a lesser extent. So double bonds do take up a little more space than single bonds. This results in slightly smaller bond angles. So something like formaldehyde, this is trigonal planar, but it has a double bond here. So this causes this bond to be around 118 degrees instead of 120, since the double bond takes up a little more space. Now triple bonds take up even more space, but anytime you've got a triple bond, it's going to be a linear molecule, so the bond angle is not affected. Okay, I mentioned this already. Lone pairs and molecules with trigonal bipyramidal geometries, the lone pairs always go on those equatorial positions. This isn't something you can expect to see on the exam. I just wanted to comment on it here. Okay, so steps so far is you first do want to draw the correct Lewis structure, then count the number of domains. The number of domains corresponds to one of the 5 electron domain geometries. Determine the approximate bond angle from the number of domains. Count the number of lone pairs. Find the combination, the molecular geometry based upon that combination, and if there are lone pairs, include a less than symbol in front of the bond angle. So here, our correct Lewis structure for ammonia, we've got 4 domains, which gives us a tetrahedral electron domain geometry, which means the bond angle is approximately 109.5 degrees. However, we've got 1 lone pair, which means the actual molecular geometry is trigonal bipyramidal, and so we're going to say the bond angle is less than 109.5 degrees. Now, for multi-center molecules, you want to take each central atom separately. So, for example, this is methanol. Methanol has 2 central atoms. The carbon and the oxygen are both central atoms. So let's start with the carbon atom. It's got 4 electron domains. Its electron domain geometry is tetrahedral, and it doesn't have any lone pairs, so its molecular geometry is also tetrahedral. So the bond angle, 109.5 degrees. Now, if we go to oxygen, it also has 4 electron domains, which makes its electron domain geometry tetrahedral. However, it's got 2 lone pairs, which makes its molecular geometry bent. Thus, the bond angle is less than 109.5 degrees. Okay, bond dipole moment. Now, I'm not going to ask you to calculate these on the exam. They may pop up on the homework, so I wanted to talk about it here. The polarity of a bond can be quantified using the dipole moment. So the dipole moment uses the Greek letter mu, so it's kind of like a U with a little thing hanging off it here. This is called mu. And it is calculated with the following equation. Mu equals Q times R, where Q is the magnitude of the partial charges, and R is the distance between the charges. Now, this dipole moment, as we learned earlier in this unit, can be drawn as a vector with the arrow pointing towards the more electronegative element. Now, this is important because here we're going to talk about overall dipoles of molecules. So when I say overall dipole, really what I'm talking about is the polarity. So earlier in this unit, we learned about polarity. We learned how there are polar covalent bonds and non-polar covalent bonds. So bonds that are polar are said to have a dipole moment. Now, not only can bonds be polar, but molecules themselves can be polar as well. So if we want to figure out whether or not a molecule is polar, whether or not it has an overall dipole moment, we need to analyze 2 things. We need to analyze, does it have polar bonds? But we also need to analyze its geometry. So let's look at carbon dioxide, for example. Carbon is our central atom here, and it's double bonded to these oxygen atoms. Now, both of these bonds are polar covalent bonds because oxygen is much more electronegative than carbon is. So the oxygen atoms are pulling the electron density towards them. So both of these bonds are polar covalent bonds, and you could say that both of these bonds have dipole moments. However, the overall dipole moment of the molecule is 0, meaning the molecule itself is nonpolar. So carbon dioxide, despite having polar covalent bonds, is a nonpolar molecule. And well, why is this? So this is where geometry comes into play. So I want you to think about that tug of war analogy again. Again, imagine the oxygen atoms here are playing tug of war on carbon. So both oxygen atoms are pulling hard on the carbon atom. They're pulling hard on those electrons and pulling them towards them. Well, the oxygen atoms, because of the geometry of the molecule, they are pulling in an exactly equal and opposite direction. So just like two teams in tug of war who are exactly the same strength as one another, right? That flag in the middle doesn't move. Same idea here, because these oxygen atoms are pulling with the same strength in the complete opposite direction. They in effect cancel each other out. These bonds cancel out, which means the molecule is nonpolar. If we look at a molecule like water, water is a polar molecule, and so the reason for this is, again, water has polar bonds, but because of its geometry, these bonds do not cancel out. Right here, these bonds are going in the complete opposite direction from one another, so if you summed these two vectors together, they would cancel out. Here, if you took these two vectors and added them together, they definitely would not cancel out. They would just make a big vector pointing in that direction. So this molecule is polar because it has polar bonds, and because of its geometry, those bonds do not cancel each other out. So again, there are a few factors that affect polarity. The molecular geometry of the atoms or the direction of bonds is important. And again, the magnitude of electronegativity differences is also very important. These vectors are magnitudes and directions. So if I looked at something like this molecule where I swapped out one of those oxygens for a sulfur, well, now the molecule becomes polar again because even though the geometry is still linear, oxygen pulls a little bit harder than sulfur does, so this molecule becomes polar. So here are some polarity rules I recommend you study and review because this will help you out a lot on the exam. Now the general rules are: first, if all terminal atoms are the same and there are no lone pairs on the central atom, the molecule is always nonpolar. So if the terminal atoms are the same and there are no lone pairs, the molecule is always nonpolar. If the terminal atoms are not all the same, the molecule is probably polar. It's highly likely it's polar. I wouldn't give you an example where it isn't, and I wouldn't try to make things complicated. If there are lone pairs on the central atom, the molecule is probably polar. So if it's bent, trigonal pyramidal, seesaw, T-shaped, or square pyramidal, these are always polar due to lone pairs that don't cancel out in a three-dimensional structure. However, if they are square planar or linear geometries, they are nonpolar if all terminal atoms are the same. Square planar and linear geometries are symmetric geometries. So if those terminal atoms are the same, then everything will cancel out, making the molecule nonpolar. So let's look at an example, or let's have you try this knowledge check question. Identify the nonpolar molecules in the following group: HBr, CH4, CHCl3, and CCl4. Okay, the correct answer is D. CH4 and CCl4 are nonpolar. So the last three, CH4, CHCl3, and CCl4, they all have a tetrahedral molecular geometry. Now CH4 and CCl4 are both nonpolar because there are no lone pairs in the central atom, and the terminal atoms are the same. Now with CHCl3, there are no lone pairs on your central atom when you draw the Lewis structure, but the terminal atoms are not the same, so CHCl3 is polar. HBr is most definitely polar since we've just got hydrogen and bromine. So D is the correct answer. Now, one thing I do want to quickly highlight on is what's interesting about polar molecules is because they are polar, they will respond to electric fields. So polar molecules will align their dipoles. If you turn on an electric field, the positive end of that molecule will turn towards the negative electric field, and the partial negative charges here will align with the positive end of the electric field. One thing I also want to mention here is, why do we care about this? Well, like dissolves like. You've probably heard this phrase before. Polar molecules will dissolve other polar molecules, whereas nonpolar molecules will dissolve other nonpolar molecules. So have you ever seen footage of something like an oil spill, where the oil just always kind of floats on the water and it kind of leaves that like black slime on the surface of the water? Well, the reason for that is because oil is typically derived and composed of these long hydrocarbons. They are non-polar molecules, whereas water is polar. So you've got the non-polar oil and the polar water, and so they won't dissolve in one another, so the oil kind of just sits on the surface. Or if you've ever had Italian dressing before, how it separates into two layers. There's an oil layer, and there's that layer on top with like all the seasonings, and that's because one of them is polar, one's non-polar, so you got to shake it up to get them to mix together temporarily. Alright, so the overall chain of deduction here is you've got your Lewis structure. So draw your Lewis structure, find the number of domains, find the electron domain geometry, then count your lone pairs, find the molecular geometry and the actual bond angle, and then finally consider the molecular geometry and consider the electronegativity values of those atoms and determine the polarity of the molecule. Okay, here are some practice problems for you to try, so I recommend pausing the video for a few minutes here. Give these problems a try on your notebook, and then when you are ready on the next slide, here are the answers. That concludes Chapter 4. I'll see you in the next video when we start getting into Chapter 5 and learning more about some advanced theories of bonding.